It is for this reason we'll consider a slightly more robust safety system that not only stops lowering the door, but also lifts it to the limits of travel when the through beam is interrupted while the door is descending. Note this ladder logic diagram includes not only a normally closed photoelectric switch that de-energizes the lowering contactor coil when triggered, but also a normally open photoelectric switch that simultaneously energizes the lifting contactor coil when triggered. I've included a mechanical interlock symbol between the two switches to indicate that when the normally open contact closes, the normally closed contact simultaneously opens. Note, as implemented, this particular configuration necessitates two-terminal electrically isolated photoelectric switches, not a single 3-terminal single-pole double-throw transfer switch with a common in both the normally open and normally closed side, as is common for some solid-state photoelectric switches, because there would be a voltage differential between the left terminals of the two switches pending the asserted state. We'll discuss photoelectric switches in greater detail in later lectures, and most likely do greater justice to our simple garage door opener circuit when we examine programmable logic controllers. Regardless, let's see how this particular circuit behaves when, in the act of lowering the door, some clueless dummy bebops underneath it. In lower mode, the lowering primary contactor is closed, as is the lower one holding contact. The lower 2 electrical interlock is open, thereby ensuring both contactors are never simultaneously energized. When the photoelectric switch is triggered into its activated opposite state by an obstruction, the normally open switch closes and the normally closed switch opens. Due to the open lower 2 electrical interlock in rung 1, it would appear that the lift contactor coil is not immediately energized. However, the open photoelectric switch in rung 4 de-energizes the lower contactor coil, and the associated contacts return to their opposite states. The lower primary contacts open, as does the lower 1 holding contact. As soon as the lower 2 electrical interlock in rung 1 closes, given the photoelectric switch is still being triggered by the obstruction, the closure of the lower 2 electrical interlock energizes the lift contactor coil, and the system immediately switches to lift mode, bypassing the stop intermediary. This is a plugging action characterized by the immediate reversal of directional rotation. When the lift contactor coil is energized, its associated contacts change states. The lift 1 holding contact closes, the lift 2 electrical interlock opens, and the primary lift contacts close. The spring-sat electrically released friction brake remains disengaged, and the motor immediately reverses direction and begins lifting the door. Note that the now closed lift 1 holding contact would maintain the energized state of the lift contactor coil even if the obstruction is removed from the path of the photoelectric through-beam scanner in the process of lifting the door. As previously, the door would continue lifting until it reached the limits of travel. The top limit switch opens when the tag strikes, and it would de-energize the lift contactor coil. The de-energized spring-set friction brake would park the suspended door in the fully open position as intended. The individual that narrowly avoided being crushed to a pulpy goo could now continue on their merry way. Let us now examine an entirely different circuit making use of a reversing motor starter. This ladder logic diagram governs the operation of a reciprocating conveyor belt that, once started and initialized with the chosen direction, continually oscillates back and forth between two limit switches. This could be utilized to perform some industrial process, like a repetitive assembly line or agitation of a product on a belt. The primary schematic, again, consists of paired contactors wired such that the forward contactor produces clockwise rotation and the reversing contactor produces counterclockwise rotation by swapping two phases. The ladder logic diagram is best examined as three functional blocks. Rungs 1 and 2 make use of a control relay that governs the starting and stopping of the whole system. Note if contact CR2 associated with the CR control relay coil is not closed, none of the remaining rungs will assert an output. Rungs 3, 4, and 5 govern the forward contactor. Rungs 6, 7, and 8 govern the reverse contactor. Note the mechanically and electrically interlocked forward and reverse contactor coils. These interlocks ensure the forward and reverse contactor are never simultaneously closed. Additionally, note the use of two mechanically interlocked limit switches, LS1 and LS2. I've colored the limit switches and annotated the mechanical interlock to purposely avoid the use of an ugly rung-spanning dashed line. Note when the normally open side of a particular limit switch closes, the normally closed side simultaneously opens. Let's walk through the ladder logic diagram and see how this system works. Assuming the system begins the day with the object to be shuttled back and forth in the center of the conveyor belt, means none of the limit switches are being triggered into their activated opposite state. An operator wishing to initiate the system presses the start push button. Via the e-stop, the stop, and the now closed start push button, the coil of the control relay is energized. When the coil of the control relay is energized, its associated contacts change to their activated opposite state. The CR1 holding contact closes, as does the CR2 contact. An operator could release the start push button, and the CR1 holding contact maintains this last asserted state. Nothing happens. An operator must now choose an initial direction. An operator can start the conveyor belt in the forward direction by pressing the forward push button. The forward contactor coil is energized. When the forward contactor coil is energized, its associated contacts are activated into their opposite state. The F1 holding contact closes, the F2 electrical interlock opens, and the primary F contacts close. The conveyor belt initiates movement in the forward direction. An operator can release the forward push button, and the now closed F1 holding contact will maintain the last asserted state. When the conveyor belt has moved long enough in the forward direction, the object to be shuttled back and forth strikes limit switch 2 at the right limits of travel. When limit switch 2 is activated, the normally closed side in rung 3 opens, and the normally open side in rung 8 closes. The now open limit switch in rung 3 de-energizes the F contactor coil, and its associated contacts return to their deactivated state. The F1 holding contact opens, removing the holding circuit. The F2 electrical interlock closes, and the F primary contacts open. Note as soon as the F2 electrical interlock closes, via the still closed limit switch 2 in rung 8, the reversing contactor coil is energized. When the reversing contactor coil is energized, its associated contacts change to their opposite states. The R2 electrical interlock opens, the R1 holding contact closes, and the reversing primary contacts close. The conveyor belt begins moving in the opposite direction. Note as soon as the object to be shuttled back and forth departs the reset region of limit switch 2, the mechanically interlocked limit switch 2 contacts will return to their deactivated states. The normally closed side in rung 3 closes, and the normally open side in rung 8 opens. Note because of the holding contact R1 in rung 7, the reverse mode is still asserted, and the conveyor belt continues moving in the reverse direction, until such time that the object to be shuttled back and forth strikes limit switch 1. The act of striking limit switch 1 closes the open side and opens the closed side. The now open limit switch in rung 6 de-energizes the reversing contactor coil, and the associated contacts return to their deactivated state. The R2 electrical interlock closes, the R1 holding contact opens, and the reversing primary contacts open. As soon as the R2 electrical interlock in rung 3 closes, the forward contactor coil is energized via the now closed limit switch in rung 5. And you guessed it, the forward mode is asserted. The F1 holding contact closes, the F2 electrical interlock opens, and the F primary contacts close. The conveyor belt changes direction yet again, and the object to be shuttled back and forth begins rightward progress. Note as the object to be shuttled back and forth departs the reset region of limit switch 1, the limit switch contacts return to their deactivated state. The normally open side in rung 5 opens, and the normally closed side in rung 6 closes. Due to the F1 holding contact, the forward mode is asserted until limit switch 2 is struck, and then the process repeats itself in the reverse direction until limit switch 1 is struck. And the process repeats itself in the forward direction until limit switch 2 is struck, and on and on and on. An operator choosing to stop this reciprocating conveyor belt at any point in its cycle simply needs to either open the stop or the e-stop, which de-energizes the control relay coil, and its associated contacts return to their deactivated state. The CR1 holding contact opens, as does the CR2 contact. The now open CR2 contact de-energizes whichever contact or coil is currently being asserted and de-energizes the motor. When an operator releases the stop push button, the system is ready to initiate yet another day of reciprocation. In summary, this circuit, making use of a reversing motor starter, selectively energizes and de-energizes the forward and reversing contactor based on the position of the object on the conveyor belt. Once initialized, it will continue to do so without the necessity of bathroom breaks, lunch breaks, or smoke breaks. Alright, this about wraps up our examination of these example circuits making use of reversing motor starters. Again, keep in mind at this point in your education, I am not asking you to design ladder logic diagrams. All I'm asking you to do is to be able to interpret existing ladder logic diagrams and determine the response given various input conditions. My intention in this lecture was to serve as a guide for a representative sample of ladder logic diagrams, utilizing some of the concepts and devices we've thus far discussed, notably reversing motor starters. In conclusion, this lecture examined a couple circuits making use of a reversing motor starter. Though their function and purpose differed, note each primary circuit made use of paired contactors wired such that the forward and reverse contactor produced opposite rotation by swapping two phases. The ladder logic made use of mechanical and electrical interlocks to ensure the forward and reversing contactor are never simultaneously energized. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.